Myself, Dr. Ganesh Acharya, Assistant Professor, Department of Chemistry, IDSG Government College, Chikmagaluru. In this lecture, I'm going to talk about an introduction to the quantum chemistry, which is a part of 6th semester PSc syllabus of Kuvempu University. The quantum mechanics or quantum chemistry is very important. It is because, the breakdown of the classical physics, the quantum mechanics, and later quantum chemistry has came to picture. In the later part of 19th century, most physicists believed that the ultimate description of the nature had already been achieved and that only the details remained to be worked out. This belief was based on the Newtonian mechanics or Maxwellian electrodynamics. But however, as soon as the experimental techniques were developed to the stage where atoms could be studied, the difficulties appeared, which could not be resolved based on the Newtonian mechanics, and even concepts of the classical physics fails in this case. So the necessary laws and concepts, that is new concepts developed over the first quarter of the 20th century are those of quantum mechanics. Hence, quantum theory ranks one of the revolutionary theories of 20th century physics. Friends, what is quantum mechanics actually? Quantum mechanics is the theory of very small objects like molecules, elementary particles, atoms, etc. So classical physics fails in this case of atoms, molecules, and elementary particles. Hence, quantum mechanics came into picture. So one of the essential differences between the classical and quantum mechanics is that the physical variables like energy, angular momentum, position, etc. can take a continuous value in the classical mechanics, that is a trajectory motion of the particle. Hence it can be continuous, but they can take discrete or quantized values in the quantum mechanics. For example, if you take the energy levels in the atoms or spin of elementary particles. In a simple sense, we can differentiate the classical and quantum mechanics as classical mechanics means everything is continuous and everything is allowed with respect to the physical quantities. But in the quantum mechanics, it is not so. Everything like the physical quantities are discrete, discontinuous, and not allowed everything. So how exactly we can differentiate the classical and quantum mechanics? Let us see. Let us differentiate the classical and quantum mechanics by taking few examples as the practical sense. So the first difference we can see as according to classical mechanics, all wavelength in light for elements are allowed. But in case of quantum mechanics, it is not like that. Every element is unique and different. That can be explained by considering the concept of the atomic spectrum. For example, if you take the hydrogen spectrum, when we take hydrogen molecules, even though hydrogen molecule contains only hydrogen atoms, it gives several bands in the atomic spectrum like Lyman, Balmer, Paschen, Piffin, bracket, etc. Why it is so? It is because of the electronic transition from one energy level to the another energy level, which are having differences in energies. That can be explained by an equation, that is E is equal to Rn into 1 over n1 square minus 1 over n2 square. That is called as Rydberg equation. If all energy levels are having the same energy, in turn it is same wavelength, then obviously it should give a single continuous spectrum. But that is not the case. Here we are observing different bands in the atomic spectrum of hydrogen atom. That shows that each element is unique and every energy level is having different discrete energies. So we can say that it is quantized. The energy or wavelength corresponding to the elements is quantized. So that is the first difference between the classical and quantum mechanics. The second difference is, as wavelength decreases, intensity increases according to the classical mechanics. But according to quantum mechanics, intensity has a maximum. We can take the concept of black body radiation. We all know that the black body is an object which can absorb all the radiation falling on it, and it can re-emit all the radiations which has fallen on it. Now, if you look at the spectrum of energy density with respect to wavelength that is shown in this picture, if you consider the classical mechanics, obviously when the black body is heated to different temperatures, as temperature increased, obviously the intensity or energy density must go up to infinity, and it is continuous. But in practice, the actual observation is, as the temperature increases, the frequency also increases, wavelength is reducing. So wavelength is increasing. So therefore, you can see that as temperature increases, the intensity reaches a maximum value. So corresponding to different temperatures, instead of getting a continuum, you will get a maximum corresponding to different wavelengths. That shows that the wavelength corresponding to a particular temperature is not same for all temperatures, but it is different for different temperatures. That shows that the energy density corresponding to that particular wavelength is not continuous, it is discrete. So therefore you can say that here the classical mechanics fails, because you will not going to observe a continuum of intensity with the increase in the temperature, but instead here you can see that the wavelength has different values, and the intensity has different maxima corresponding to different temperatures. So therefore you can say that the energy corresponding to the black body radiation is not continuous, it is discrete. So it is quantized. So classical mechanics or classical physics fails here. And the next difference is by considering the photoelectric effect here. According to classical mechanics, as energy increases, the number of electrons removed must also increase. Whatever may be the energy, the electrons can be removed from the surface of a metal. So that is called as photoelectric effect. But in practice, in the actual observation, it is not so. In the quantum mechanics, it says that the removal of electrons is only above the threshold energy, but not for all the possible energies. So energy, the frequency corresponding to the removal of electron is fixed, and it is called as a threshold energy. So photoelectric emission should occur for any frequency of light, no concept of threshold frequency in case of classical physics. But in the quantum physics or quantum mechanics, there is a certain minimum frequency nu naught of incident radiation, below which there is no emission of photoelectrons regardless of the intensity of the incident radiation. So this frequency is known as threshold frequency, which depends on the material and the nature of the emitting surface. So therefore, here also the classical physics fails, or classical mechanics fails, and if at all energy can be able to remove electrons from the surface of a metal, obviously we can say that the values of energy is continuous. If it is discrete, then only there must be a threshold frequency after which there will be removal of electrons. Hence, the energy is quantized, because not all energy can be able to remove electrons from the surface of a metal, but only a certain minimum frequency required for the removal of electrons. Hence, the energy is quantized. So the concept. The next difference is, according to classical mechanics, the radiation can be either wave or a particle, but in the quantum mechanics, it can be both the wave as well as particle. Now, when you consider these two equations, E is equal to mc square and E is equal to h nu, when you combine these two, you will going to get an equation lambda is equal to h over mv, which is called as de Broglie equation. Here, lambda, that is wavelength, and mass, and the velocity. You can see that as the mass increases, the wave character decreases. As the particle size goes on decreases, its wave character increases. So therefore, you can say that the radiation can either be, it can behave both as wave and also a particle. It depends upon the mass of the object according to quantum mechanics. And the next difference is position and velocity can be known according to classical mechanics for any object, moving object. But this is not applicable for the minute particles like electrons or atoms, etc. So according to quantum mechanics, only you can determine either position or momentum, but not both simultaneously and precisely. This is called as Heisenberg's uncertainty principle. So therefore, according to quantum mechanics, you can determine either position or momentum, but not both simultaneously and precisely. Now, let us look at some of the postulates of quantum mechanics. The relationship between quantum mechanics and operators has helped to present the concepts in the form of postulates. These postulates are as follows. The first postulate is the state of a system is completely described by a wave function. So what is a wave function? Actually, wave function means it is a similar term as that of the amplitude of wave in the classical mechanics. And in the quantum mechanics, you can describe the state of a system completely by using a wave function. And the wave function must be finite everywhere, and it is single valued, and it is continuous, and it must be normalized. So these are some of the properties of wave function. And the second postulate is for every observable in the classical mechanics, there corresponds a linear Hermitian operator in the quantum mechanics. That is for every observable, like position, kinetic energy, potential energy, total energy, etc. You must be able to observe an operator in the quantum mechanics. For example, if you take momentum as a physical observable, the operator corresponding to that is minus I h cross dou by dou x. When you take the total energy, you can take the term as Hamiltonian operator, that is H is equal to T plus V, that is total energy is equal to kinetic energy plus potential energy, and the operator corresponding to that is minus H cross square by 2m dou square by dou x square plus Vx. So like this, for every observable, there corresponds an operator in the quantum mechanics. This is the second postulate. And the third postulate is in any measurement of the observable associated with operator, the only values that will ever be observed are the eigenvalues which satisfy the eigenvalue equation, that is a cap psi is equal to a psi. So when you operate a wave function with a suitable operator, you will going to get a value, constant value multiplied by the same wave function, that is called as eigenvalue equation. And here small a is called as eigenvalue, and psi is called eigenfunction, and a cap is the operator. Okay. And the fourth postulate is if a system is in the state described by a normalized wave function, then the average value of an observable corresponding to the wave function is given by, here a is equal to integration of minus infinity to plus infinity psi star a cap psi divided by integration of psi star into psi into dx. So this is the average value of an observable according to the fourth postulate. And the fifth postulate is the wave function or state function of the system evolves in time according to the time-dependent Schrodinger equation, and it is given by I h cross dou psi by dou t is equal to h cap psi. This is by simple combination of this equation, a Hamiltonian equation, that is h psi is equal to E psi. Here the total energy is the sum of kinetic and potential energy, and the corresponding equation here it is given by J h cross dou psi by dou t is equal to minus h cross square by 2m dou square psi by dou x square plus V psi. And the last and the sixth postulate is the total wave function must be antisymmetric with respect to the interchange of all coordinates. So friends, you can also go through these references, that is Fundamentals of Quantum Chemistry by Michael Mueller, Undergraduate Quantum Chemistry by Jussi Lorenta, Elementary Quantum Mechanics by David S. Saxon, Quantum Chemistry by Donald McQuarrie. Thank you very much for watching this video. We shall meet soon in the next video. Thank you very much.